Okay, good afternoon. First, I'd like to thank Mauro and Wilson for inviting me to this very nice conference. I'll talk about conformal vortex crystals. This is a work performed mostly by my PhD student. Jaime Menezes, who is also presenting a poster later this evening. This work is under consideration by the referees, but you can download a preprint in archive. So the outline of my talk, I'll first reveal homogeneous and graded vortex distributions and how topological defects can stabilize gradients of vortex distributions. And then I'll move to what we call conformal vortex crystal, which is essentially a topological defect-free state of vortices that is non-uniform but keeps the crystalline phase. Then I'll talk about the thermostability of these states and possible experimental realizations. Okay, so this is a very old image, one of the first images of vortices and superconductors. This is a more recent one. So vortices, they quite roughly, in conventional materials at least, they interact isotropically, then they try to be as far away from each other as possible, and then there is compression of external magnetic field, and all these ingredients gives rise to this Abrikosov lattice, which has triangular symmetry. But then you can also induce non-uniform distribution of vortices. This occurs naturally if you build a critical state in a homogeneous superconductor. When you increase field, then field comes in and builds up gradients of flux. But recently, people have been trying to induce flux gradients in a more ordered way. So I believe one of the aims of such kind of studies is to enhance the critical currents, because vortices would be in a gradient state, like in a beam critical state, but would keep, at least locally, their natural symmetry, the hexagonal symmetry. So several groups, different groups, worked on these so-called graded pinning structures. This one in particular is very interesting because the distribution is locally hexagonal. And they have been demonstrating that indeed you have very efficient pinning when you subject vortices to such kind of distributions. Well, these are measurements, and okay, these are measurements, but it was also anticipated by molecular dynamics simulations by Ray and Charles and Cynthia. And what they showed is that indeed you have an enhancement of the critical current. The width of the magnetization curve is larger when you have this kind of structure, the conformal graded pinning distribution. So an interesting thing of this kind of material is that vortices, the incoming vortices, they distribute in uneven way. So we have regions where you have an almost matching condition of vortices, while other regions there are no vortices sitting in the pinning sites. So the authors think that this probably explains the high efficiency of the critical current in a broad range of field, because then the vortices can adapt and match locally to the pinning distribution. Okay, but I'll talk about not such kinds of non-uniform crystals induced by two-dimensional potential. But actually, we are looking for self-organized vortex distributions in homogeneous systems. So the idea is to use a one-dimensional potential and check if the two-dimensional distribution of the vortices would follow such kinds of structure without the necessity of trapping vortices locally. So this is a very weak pinning. It's also a work of Assman group in the 60s. It's a very weak pinning material, and this is the critical state in this material. So you can see that vortex density is high here and more or less low here, and there is a gradient here from left to right. And there is a kind of topological defects distribution all over. And the authors calculated the distribution of these defects and demonstrated that it agrees with conventional theory of crystalline defects, that in order to keep this gradient, you need a certain distribution of defects. Okay, but what topological defects do? Here you have disclinations. What it does is to bend the whole lattice. So this costs a lot of energy in order to fit a pentagon here in this point. And you have the opposite situation where you can fit a heptagon here, and then you have to insert material, let's say. And this also costs a huge amount of energy. So typically, these defects, they appear in pairs, so-called dislocations. And sometimes these dislocations, they form a chain of material like this, and then you have grain boundaries. So these are typical defect structures in crystalline materials, in two-dimensional crystalline materials. But one important thing of topological defects is that they can stabilize curvature. So if you want to search for a non-homogeneous distribution of vortices, the system has to cope with curvature of the lattice lines. So for that, you need a specific distribution of topological defects. So you can see here in these simulations by Leonardo Cabral and François Peters, more than 10 years ago. These are actually vortices in a superconducting disk. So you see that when you increase the number of vortices, you have topological defects migrating to the bulk of the sample. So the same happens also with plasmas. These are simulations on Coulomb charge, on harmonic trap. So you can see that for not very large number of particles, you have a few defects here, and the surface behaves in a different way as the bulk. But when they increase the number of particles, they can accommodate this. Sorry. Yeah. You can accommodate this very nice bending of the lattice. So the point is it possible to build a kind of crystal, two-dimensional crystal, where you have really large amounts of particles or vortices that with a gradient, but without topological defects in the middle? Well, the answer is yes, at least for a very selected group of systems. So to my knowledge, this is the only system that exhibits this property, at least the only system of particles that exhibit these properties. This is a soft matter experiment with magnetic particles interacting via a dipole interaction. And what the authors did was to apply a field to polarize the particles, and then they just tilt the table so that the particles compressed by gravity, and they form this structure. So if you look close, you see that each particle here has precisely 6 neighbors. And then they realized that, in fact, you can map this back to a triangular lattice using the logarithmic map. This is a conformal mapping that preserves angle. Okay? So in the case of their experiment, this transformation is only approximate. Another important point is that the logarithmic map is the only possible that can give a stable configuration like this. Okay, so the idea is to check if vortices can form those kind of structures. So the first step is to compute what's the density profile of vortices for this kind of conformal transformation. And then we use a simple continuum approximation for the energy functional of vortices. This is the density, this is the potential, this is the interaction potential. So what we want to find is which kind of external potential can accommodate this, precisely this density profile. So if you minimize this, you get this very simple expression. This is just a balance condition for the vortices. So this is the interaction potential, this is the external potential. And this constant here is a Lagrange multiplier. It's just a constant. Well, if vortices interact via Bessel functions, like in the bulk, so the interactions are short range, and then you can approximate this equation. You can take this off the integral, and what you have is that the external potential mimics the density. So the density profile that you want is exponential, and then the potential that you need will also be approximately exponential. Okay? So this is a necessary condition for accommodating vortex distribution that has the correct density. It doesn't mean that you will have a conformal crystal, because you can end up with a non-uniform glass or a non-uniform polycrystal or whatever, but not necessarily a conformal crystal. So to check that, you need to make a detailed minimization procedure. That's what we did. We did minimization via simulated annealing using a molecular dynamics simulation. And this is one of the configurations that we get. So you see that the vortices form this nice arch pillar structure. And these hexagons here, they are Voronoi constructions. And you see that most part of the sample is free of defects. So defects simply accumulate in the boundaries of the sample. So these structures here, they are high-angle grain boundaries. They have non-zero net charge, which is a positive charge. It's a pentagon. If you see, there are 1, 2, 3, 4, 5 dipoles, but with an extra charge, each of them. Okay. And these so-called scars, they are responsible for accommodating this structure and a kind of depletion zone. So the vortices here, below these scars, they distribute in Abrikosov lattice, conventional uniform triangular lattice. Okay, so to check how conformal is the final configuration, we do the inverse map. Okay, so this is just a mathematical construction. This is the physical simulation, and then we map back to a complex plane from which the transformation is performed. So we end with almost perfect triangular lattice. That's the idea of the conformal transformation in the end. So there is some deformation here. I will explain it a little bit later. Not all configurations are single crystal like this one. This is a single conformal crystal, okay? But some configurations, they have this kind of twin boundary. And then we repeat this minimization procedure for 50 times. And this is the distribution of configurations that we get. This configuration here is a perfect single crystal, conformal crystal, without any of these lines. And here you have samples with 1 line, 2 lines, 3 lines, and 4 lines. So the perfect single crystalline phase is the most frequent one. It's difficult to compare the energy because the energy is very similar to each other, because these dipole structures, these dipole chains, they cost little energy. So it's hard to say which is the minimum energy in this case. So the idea is to check which is the most frequent one. Okay, so those results were for bulk superconductors. What if you have a thin film and vortices interact long range? Okay. So if vortices interact via a long range potential, you have to consider the full non-local character of this equation here. So you need to put the interaction potential here and perform the integration. And here, for a comparison, we plot the density of vortices, the density profile of vortices resulting from the simulation. Here is the potential energy, the external potential. This is for the previous situation, where you have vortices in bulk superconductors interacting via Bessel potential. But for thin film, the potential is completely different. Okay? It's completely different. This means that, for instance, if you try to accommodate vortices with a conformal pinning array in the bulk, this is would be a stable configuration. But in a thin film, it would not be a stable, it would be metastable. So we also observe conformal structure. We make the inverse map and also observe the triangular lattice. So it also works for long-range interactions. So this simple method you can use for particles interacting via short-range or long-range potentials. Okay, so important question is, are these conformal crystals stable? So we analyzed in detail the number of defects as a function of temperature. Okay, so what we observe is that for low temperatures at this plateau here, we have this conformal crystal, but above a certain critical temperature, these lines, defect lines, start to nucleate throughout the material, and they proliferate, and you have a kind of conformal polycrystal. So you have small conformal crystals throughout the sample. And the melting transition is in a much higher temperature. Okay. Okay, but coming back to the bulk case, we can think of what would be the configuration, the vortex configuration, if the external potential is non-conformal. Okay? So this is the conformal case. The potential was built to have the conformal vortex crystal. This is a potential, a simple linear potential. This is equivalent to the experiments with magnetic spheres, because the gravitational potential is linear, right? And this one is with inverse curvature of the first one. So what you see here is that the linear potential can accommodate a crystal that resembles the conformal crystal. But this is not exactly conformal. If you do the inverse map, it won't go to a triangular lattice, okay? And this one, with the inverse curvature, you see that there is a phase separation here. You have Abrikosov lattice here, and here is more or less conformal lattice. A possible experimental realization. One thing that came to our minds was a 20-year-old experiment by the group in Geneva, where they have very good YBCO crystal with twin boundaries, and they did some experiment with magnetic field, with increasing field and then decreasing field. And when they decrease the field, vortices that are close to the boundary, they go out. And then you have a region without vortices, and the other region you have vortices. So you can play around with the density of vortices on one side of the boundary and the other side of the boundary, because the twin boundary is a very strong pinning line center. So the idea is to use this to trap vortices in the twin boundaries and then apply a current and compress the vortices. Okay? So we did just that in the simulation, of course, and we get this quasi-conformal crystal. So you see that each vortex has more or less 6 neighbors. You can look at better in the movie here. Oops, sorry. So you compress, the number of defects increase a lot, and then start to heal in a self-organized manner. So in the end, you have this structure of curved lines and these grain boundaries here. Okay, so that's my conclusion. Sorry. Thank you very much for your attention.